So section 3.2, we're going to talk about two theorems, Rolle's theorem and the mean value theorem. The mean value theorem is one of the few theorems in our course that we actually use by name on a frequent basis. We had one in the last chapter called the intermediate value theorem, so that comes up quite a bit, and we use that by name. The mean value theorem is another. Rolle's theorem is really just a way for us to kind of introduce this idea of the mean value theorem. They're very similar. Rolle's theorem is just a specific example of, really a specific example of the mean value theorem applied. And I think if we do Rolle's theorem, it makes understanding the mean value theorem a little bit easier. So let's take a look at Rolle's theorem to start with. All right, and Rolle's theorem says if f is continuous and differentiable on this closed function from a to b, and f of a equals f of b, then there is at least one number c in that interval ab such that f prime of c equals 0. So let's think about what this means. F is continuous and differentiable. So that means that there are no holes or jumps or asymptotes or discontinuities of any kind in f of x. And it means that differentiable, for now, we'll just kind of leave it as it's smooth. So there's no sharp turns and there's no discontinuities. Okay, so it's continuous and differentiable on this interval, and f of a equals f of b. So that means that if I choose an a value here, here's my f of a, and I have to have a b value that gives me a function value f of b that is at the same height, the same y value as f of a. Alright, so these need to be at the same height. Alright, so if those things are true, f is continuous and differentiable and f of a equals f of b, then there is at least one number c. So there's one x value c in this interval here. So there's some c in here such that f prime of c equals 0. And that means that since the overall change, or the average rate of change between a and b is 0, you can see that the slope of this line going from this point to this point is 0. There has to be somewhere along this function where the derivative is also equal to 0. That's what Rolle's theorem tells us. It does not tell us where the c value is. It just tells us that there's a c value somewhere in there on that interval where the derivative is equal to 0. All right, so the kind of example we might have is if Rolle's theorem if Rolle's theorem applies, find all values of c such that f prime of c equals 0. And they give us this function. All right, so when we apply Rolle's theorem, we have to state these conditions are met. So this function, it's just a quadratic. I know it's continuous and differentiable on the interval they gave me from 0 to 3. All right, so I plug in 0. I get f of 0 and f of 3. I find that both f of 0 and f of 3 are equal to 2. So my 2 points are at the same height. So the average rate of change from one point to the other is equal to 0. And that means that Rolle's theorem applies. Now I want to find out where that derivative is equal to 0. So I want to find the values of c such that f prime of c equals 0. So I have to take the derivative of the original function and set it equal to 0. And here I just get, when I take the derivative, I just get a linear equation set equal to 0. I solve for x, I get 3 over 2. So I find that x equals 3 over 2. I have to make sure that that's in the interval that I was given. So the interval was from 0 to 3. Yes, indeed, 3 over 2 is in that interval, so that's my answer. That's the c value for which the derivative is equal to 0. The next one is the mean value theorem. So the mean value theorem is in a way kind of an extension of Rolle's theorem. Rolle's theorem said if we had 2 points that were at the same height, the average rate of change between those points is 0, then somewhere between those two x values there was an x value that would give us a derivative equal to 0. All right? And the mean value theorem kind of takes that and turns it on its side. So here's the mean value theorem. If f is continuous and differentiable, so the same two conditions, continuous and differentiable on the closed interval from a to b, then there exists at least one number c in that interval such that f prime of c equals, look at what this is, f of b minus f of a over b minus a. So that might look familiar. If it doesn't, let's take a look here and draw this out. So here's my a value. I'm going to choose a b value here. Here's f of a. Here's f of b. So I can draw that secant line just to take a look here. All right. This point is located at a, f of a. A is the x value, f of a is the y value. This point is located at b, f of b. Again, the x value and the y value. So when we look at this expression, this is really just a difference quotient. So we are taking y minus y over x minus x. This is the average slope, or the average rate of change between this point and that point. And what the mean value theorem says is there's somewhere between a and b where the derivative of this function is going to equal that average slope. So here, it might be right about here. So these lines are pretty close to parallel. So this, in this case, would be the c value that gives us that derivative equal to the average rate of change. All right, so the key here is that the mean value theorem states that the instantaneous rate of change, this got cut off a little bit, but this is instantaneous rate of change equals the average rate of change somewhere in that interval. So this example, if the MVT applies, find all values of c such that f prime of c equals f of b minus f of a over b minus a. Remember, this is just the final statement of the mean value theorem. It means the instantaneous rate of change at some x value c is going to be equal to the average rate of change between the point at a, at x equals a, and the point at x equals b. So here's the function they give us, x cubed minus x squared minus 2x on the interval from -1 to 1. So we know that this function is continuous and differentiable on the interval from -1 to 1. It's just a cubic, so it's continuous and differentiable everywhere. So we have to set up, we're trying to find where f prime of c is equal to this average rate of change. So I just plug in f of 1 minus f of -1 over 1 minus -1. I'm just using this formula right here. So I plug in 1 here, I get -2 as my function value. I plug in -1, I get 0 as my function value. And then of course 1 plus 1 is 2. So the average rate of change between those two places on the graph is -1. So I'm trying to find out where f prime of c is equal to -1. So I take the derivative of the original function, that x cubed minus x squared minus 2x. I take the derivative of that, set it equal to -1, and then I'm going to solve that. So here I get this quadratic equal to 0. I factor the quadratic. I actually get two answers here. I get x equals -1/3 and x equals 1. So take a second and think about maybe why we have to discard that x equals 1. Right, x equals 1 can't be one of our c values because it's one of the endpoints, and the endpoints are not included in the mean value theorem. Right, remember if we look up at the mean value theorem here, it says there exists at least one number c in this open interval from a to b that omits the endpoints. All right, so when we find the x value is one of the endpoints, we have to omit it. Our c value, that in this case, that we found after knowing that its existence was guaranteed by the mean value theorem, is -1/3.